So we are on page 11, looking at gas laws, which you did over Christmas, but maybe you have forgotten, so we're going to do a quick review of them. Okay, so Boyle's law has to do with pressure and volume. So what happens to pressure, this is Boyle's law here, if I take a small container with some gas in it and I make it bigger? What happens to the pressure? Remember, pressure is how often and how hard the particles bash into the walls. So pressure is how often, how hard particles bash into the walls. So if I start with 5 particles in a small space and I finish with 5 particles in a big space, yeah, the pressure is going to decrease. So as volume increases, pressure decreases. And that means that pressure is it directly or inversely proportional to volume? Inversely. So if we were to graph that, my independent variable would be volume, because I'm changing the volume, and my dependent variable would be pressure. And as volume increases, pressure decreases, and that's going to look like that. That is a 1 over x kind of function, okay? Now our equation for Boyle's law is that P1 V1 is equal to P2 V2. And if you're like, dear God, this is page 11, do I need to memorize all of these? No. Okay, I will show you how you can derive them all from the, what do you call it? What are those kind of ideal gas equation, which is given on your data sheet, okay? All right, and what are we keeping constant here? Well, if we think about our ideal gas equation, PV equals nRT, what does N stand for? That's number of moles, okay? R is the gas constant, which is given to you on your data sheet, okay? And T, of course, is the temperature. So P and V are the things that are changing in that equation. That means the 3 things that must be constant are, well, obviously, I'm not even going to mention the gas constant because it is a constant, right? We're not keeping it constant, it simply is a constant. But we have to keep N, the number of moles, the same. And we have to keep T, the temperature, the same, in order for Boyle's law to work out as a nice 1 over x relationship. Charles' law. Okay, so we are going to take our little box full of molecules, and now we are going to put underneath it a flame. Okay, so we're now heating it. So we are increasing the temperature. Oh, and actually this one, I'm sorry, this one should have a little piston at the top, a movable piston. what's going to happen to the volume as we increase the temperature? It's going to go up because the particles are going to move faster. And they will, are we good? Huh? Okay, so the particles are going to move faster. They're going to bash into the piston with more force. And so they're basically going to be pushing upward on that piston, and the volume will expand. So volume is going to increase as temperature increases, and volume is therefore, is it inversely or directly proportional to temperature? Directly. So if we increase the temperature, temperature is our, what do we call that? Independent variable, and volume is our dependent variable, and those go up like that. And sorry? No, you're right. Yeah, so it's going to be V1 over T1 is equal to V2 over T2. And you can think your way through these problems. You can, you know what I mean? Like you can think about, oh, if I have a box and I expand the volume of the box, what happens to the pressure? If I'm thinking about volume, I have to have like a changeable volume, so I would need to have that movable piston. What would happen if I put a flame under it? You can kind of like, it makes logical sense, I think, that it, you know, expands, right? So you don't need to memorize these per se, okay? And so what are we keeping constant when we are applying Charles' law? Well, obviously the gas constant. What else? Number of moles and the pressure, okay? Now the thing about when we heat this, those particles on the inside are going to push up with a certain amount of pressure. The piston will stop moving when the pressure is equal to the what? Atmospheric pressure, okay? So we will have a certain pressure pushing downwards, and then it will stop expanding once we hit that. So the pressure is being kept constant. It's going to be equal to, say, the atmospheric pressure, okay? Yeah. Oh, that's exciting. Well, okay. I don't know. I've given away all my books. So page 9 is supposed to be page 11. What did you say there? So let's see. We have page 10, which is D. Oh, the one right before it. Oh, it says page 11, and that should be page 9. Page 9. Thank you very much. Yeah, so you'd be looking and be like, that's not page 11. Okay, thank you so much. That's good. All right, Gay-Lussac's law. You don't need to know the name of any of these laws. AP doesn't care if you know the name. They just care if you heat it, it expands, right? They don't care if you know the name. All right. What happens to pressure as we are changing the temperature? Now, if this is the case, if we're changing temperature and we're saying what happens to pressure, what do we have to be keeping constant here? Remember, we have PV equals nRT, and we are looking only at how pressure relates to temperature. Therefore, what do we need to keep constant? N and V, which means this time there is no movable piston. Yes? This time we have a little box, and it does not have a movable piston, and now we're going to heat it. All right, there's our little flame. And what will happen to pressure as we increase the temperature? It's going to get higher. Why? Yeah, so as temperature increases, the particles move faster. And they collide more frequently and with the walls more frequently and with more energy. This means that pressure is directly or inversely proportional to T. Directly. So as temperature increases, temperature is our independent variable, the pressure will also increase. What is that law going to look like? P1 over T1 equals P2 over T2. And what you'll notice is when you have a direct relationship, the two variables are one over the other, okay? And when you have an inverse relationship, the two variables are right beside each other. Because as one goes up, the other goes down. That's how they stay equal to one another, okay? Avogadro'S Law. Volume is proportional to N. So if I take my container with a piston in it, and what happens if I now put more particles in it? 1, 2, 3, 4, 5. Da, da, da. What will happen to the piston? It's going to go up because you have more particles colliding with the piston, and so it's going to go up until the pressure equals the atmospheric pressure. Okay. So as N increases, V increases. Okay, so more particles are going to collide with the piston, therefore the pressure is going to increase, but then the piston is going to move until the pressure is once again equal to the pressure of the atmosphere. Okay, so we are keeping pressure constant. I mean, I know it does change initially, but then it eventually evens out. Okay, so pressure is staying constant, N is not staying constant. So what's the other thing that must be staying constant here? Temperature. And volume is directly proportional to N. So as we can increase N, our independent variable, the volume will increase. Oh, I didn't draw my graph up here. That should go there. So basically everything is a direct relationship except for P and V, okay? Now, the combined gas law we're going to come to in a minute. Let's write our ideal gas law to start with. And we have PV equals nRT. This is given to you on your AP sheet. However, if you want to remember it, I always call it the pervert equation, okay? Because it kind of looks like pervert, but there's an N in the middle, okay? But nobody forgets that it's the pervert equation. And I am not the only person to come up with this. I've seen many videos where people refer to it as the pervert equation, okay? You remember things when they're slightly inappropriate, right? All right, so we've got that. The only thing that's kept constant in that one is R, so you can be mucking about with V and P, and you can change all kinds of things all at once. Now, if you would like the combined gas law, you just take your ideal gas law and you leave out the R and you write PV equals NT over PV equals, I won't put another equal sign there, equals NT. And here you have P1, V1, P2, V2, or C. Is that right? Oh, I'm such a dummy. I'm so sorry. I'm just wrong. What we're going to do is we're going to solve this for N. Brain's not awake this morning. We're going to solve for N. So N is equal to, try solving for N. Make sure you can do your algebra. It's just PV over RT. Am I doing this for, oh my God, no, we should be solving for R. What is wrong with me? Solve for R. Solve for R. I'm sorry, my brain is not awake this morning. So we're solving for R. We're solving for R. So R is equal to PV over NT. Okay, I think we're on the right track now. Yes, we are. And so R is going to be the same no matter whether you're at condition 1 or whether you're at condition 2. So R before is going to equal R after. In other words, R1 is going to equal R2 because it's a constant. And so this allows us to say we have P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And sometimes that's more convenient to use than the ideal gas equation. It just depends on what, like you could probably use either of them to solve your problem, but depends what you like, okay? That was kind of painful. I'm sorry that took quite so long as it did, but you know. Yes? Avogadro'S law. Oh yeah, Avogadro'S law. What is Avogadro'S law? We have N and V which are directly proportional, so it's N1 over V1 equals N2 over V2. You can always take those equations and flip them upside down as well, right? You could have V1 over N1 equals V2 over N2. The ratios will be constant. So let's say you were solving for V2, it might be easier to flip it over. Okay. So you have some exercises to do here. How about you just try some of those? And yeah, just get through whatever you can get through in the next 5 minutes, and then we'll see you next week. Sound good? Cool.